The first definition on this page is inner product. And this is an abstract concept. It's a new way of thinking of times or product. A product takes in two objects. We say A times B, meaning we need an A and a B. Or in the case of the way things look on this handout a lot, we're using lowercase letters to refer to vectors, things like U and V. And we're also still using the Greek alphabet to refer to scalars, or real or complex numbers. Now, because this is written on your handout for complex numbers, there's a bit that we need to talk about so that you know some background on complex numbers. Maybe you already know all this stuff and you can skip the first part of this clip. In general, vectors dot product can spit out a complex number. And so you'll see some notation on the handout when there is a bar over something. If we have a number that's a complex number, it means it has a real part and an imaginary part, an A and a B, A plus BI. The bar means switch the sign of the imaginary part. That's called conjugate, just like the word that's in parentheses on the handout is conjugate. If this is A minus BI, then conjugate would change it to an A plus BI. It always just switches the sign of the imaginary part. Notice that if this were a real number, meaning that B is 0 means this is a real number, then changing the sign of 0 doesn't do anything. So now, your first time, or maybe even your first 7 times, going through this handout, if you just think in terms of real numbers and don't worry about complex numbers, then bars don't do anything, and that's okay. Most of what we do is real numbers anyway, for the sake of completeness, because this is printed on the page, and you can refer to it for the rest of your math lives. It is important that you see how this goes for complex numbers, but as you learn it, it's easier to learn it for real numbers, and so for real numbers, you can ignore the bar. Another note on complex numbers is that if you see a star above a matrix, star is the complex version of transpose. Every time you see a matrix A star, you should just think A transpose, but in the complex world, we put a bar over things when we transpose them. So to walk us through these three properties of inner product, I have some examples up on the whiteboard here. The first example is the dot product in Rn, which you can see on the next page, how the mechanics of this goes. But just to get an idea of these three properties, the three properties are what defines an inner product. This is not the only example of an inner product. Anything with the three properties on your handout makes an inner product. The three properties in terms of this example, the first one is symmetry. And notice if these are all real numbers, the bars don't matter, and so I didn't put the bars on the handout here, or on the whiteboard here. Symmetry is kind of like a commutative property. We say that U times V equals V times U. You can work out the details for the vector dot product, and you'll find that U dot V equals V dot U works. The second property is linear in the first argument. You could think of this as like a distributive property. These are all of our linear things that we like to do. Whenever we have two things added together, we break them into the two parts. That's one of our linear operations, is adding. And whenever we have a scalar, a constant, we take constants outside. That's our second linear operation. The alpha comes outside, the beta goes outside. The third property is a fascinating one. Sometimes they call it separation. Separation. And the idea of that property is that anything times itself is positive. It's like if you square something, it's positive. Of course, this isn't squaring a vector. This is U dot itself, or U dot U. Slightly different from just saying square a vector, because there are some mechanics involved in this. And again, for dot product, the mechanics are on the second page. This is just an example of how to write this property for a concrete example. Notice that also U dot U is 0 implies that U itself has to be 0. The only time you can square something, if you're thinking of squared, and it is 0 is if that thing itself is 0. And also then we get that if u is 0, dotting 0, 0 dot 0 is 0. This goes both ways down here. So this is one example. I will do another example on the whiteboard that is a little bit more diverse or unfamiliar. Here is that other example. For two functions, and L2 just means that you can integrate two of them on the interval a to b. This is the least to worry about in the notation. Just think of functions, f and g. F and g are functions. Look at how if you integrate two functions from a to b, first of all, you get a number. You don't get a function back because at the end, the fundamental theorem of calculus says that you plug in b and a. So this does indeed, multiplying functions and integrating gives you a number, and if these are functions, real valued functions, if you switch the order when you integrate them, that doesn't change the result that you get. That's a symmetry. Functions are behaving like vectors. Same thing with these linear operations. You can always break up two integrals, the fh and the gh, and you can always pull the alpha and the beta outside. I actually didn't pull them outside the integral, but we at least still could pull them outside of the f times h and the g times h. And look also, then if you integrate f with itself, like an f times f, you get f squared. F squared is positive. If you integrate a positive thing, is that area under a positive curve going to be positive? And look for yourselves, or draw some pictures for yourselves to see what would the condition of f have to be. In order for the integral, the area under the curve to be 0, what would f have to be? So this is the idea of inner product, is that, yes, this is basically a linear product with these special properties, but vectors aren't the only things that behave this way. That's why it's nice to have on this first page a nice abstract definition.